go first day is our 8 days, 1 day, so there are no vacations for you. And in that case, so I will present you the first homework on Wednesday, okay? So because today is Sunday, and if I just issue you the homework and you have only 2 days to finish it, so I think I will issue the homework for the today's class and the Wednesday's class together and to you, and you can just spend the whole, you can choose 1 day in either of the 8 days of the holidays to finish the work, okay? Okay, so let's get started with lecture 2. We can just go back to these lectures and just take a quick review, okay?
Complex law.
The complex, figures, right? The time domain and this is the time domain, and just to it's the method is designed for analyzing the okay, thank you. So it's designed for analyzing the transient state estimation, right? And the phasor representations is used for analyzing the steady state state estimation. So that for either the So it's either the features, electricity, either features in the electric fields, so like the voltage or the current, either one can be expressed by the phasor domain of the phasor representation or the time representation. So the phasor representations, this is the 1, 2, 3, 4, 4 different forms to express some features, some characters, or some variables. So in this case, we can just to find that the phasor domain of the phasor representations of the variables is maybe easier to understand or just to analyze. So let's compare with the time analysis or time representation. So resistance, and reactance. So this is the major 3 variables in these lectures in the phase domain. So this is the example. So we're just go through. So this is the one of the most important variables in the power system analysis, the complex power. So maybe here's one thing maybe I forgot to inform you that about this star. Star, it means the conjugate the complex variables. You know this? You can substitute and the negative in both here, right? The plus is minus, so minus is plus. So this is
45 degrees.
Minus 45 degrees. So this star means that substitute from here to here. Substitute use its conjugate the complex numbers. Okay. So this is explanations by mathematics.
Like this one.
Yes, it's of course. So I think it's several different explanations for this. You can just use you can just use your just the vectors.
This one is for 1 plus 1 this is 1 minus 1.
Yes, of course. So I just would like to emphasize that this is only just for the conjugate, and this is what is named in the mathematics. So this is a triangular, it's a very good triangular wedge. So the complex power, the reactive power, the active power, reactive power, that the active power, reactive power. So so in some questions, you can even just to solve the questions using the geometry method, right? I will also present you some examples in the geometry. So using this triangular, you can just calculate the reactive and active power very easy ways. Right? It's very easy to understand in this form. Power factors. Okay. So this is an example. And this is another locations here. We call it with 1-line diagrams. It range from our previous expressions of the situation. Yes, this one is actually more frequently used in the power analysis, and the previous just like the security expression of this is more frequently used in the security theory. So it's just in the different classes. So do you remember this? When should we add these compactors here?
Yeah. Sure.
Yeah, just to present and provide. Do you know this?
I made the simulation of
how work? Okay, so
I have one question, sir. This first bus line is the voltage is 44.94, but second bus line is 40 kV.
Yeah.
So this 4.94 is lost. Is the active power is lost?
Yeah. Actually, there will be two situations. The first one we call it the ideal situation, right? The ideal situation. So no matter how long this transmission line is, we will assume that there is absolutely no noise, no animals here, right? But this is the real situations. So in the real applications, we cannot. Yeah, you know. All the transmission lines made by different materials where still have some losses to some extent, different in different levels. But however, so the loss made by the transmission line cannot be lost anymore. Yeah. Especially when the transmission line is very long transmission lines, the length of those line is under. So the loss cannot be ignored. This is why there is a difference between these two buses, the voltage of these buses.
Because the first bus is 44.94, almost 45, and the second bus is 40.
Yeah, you can just imagine, this is transmission line without any losses, but here is the resistors. Oh, okay, so there is impedance. Also to know exactly impedance here,
make it loss.
Yeah. So everything is prepared or is established for you to analyze all the questions in a more conveniently. So of course, in power systems, this here, this might also be a resistors or might be the inductance. So we call it the shunt, right? The shunt resistor, the shunt capacitors, and just to make difference with the other shunt with the other impedance in the transmission line. So the shunt impedance were generally just grounded. So this is why the reactive compensation is important, because so the transmission line, it cannot be viewed as the ideal, can be viewed to applied in the ideal situations in our real world, right? So that's why the reactive compensation is needed. Or if we just to compute everything in the ideal environment or ideal scenarios, so the reactive compensation is noted. No need to noted anymore. This is the power, that is the direction examples. And this is the photo of the shunt capacitors. Actually, the very old styles, but it's in the same series, in the same work process. Okay, so we're gonna start here because in the previous classes, I think it's maybe a little bit limited time to introduce this one. Okay, so we can start here. So the balanced three-phase systems, right? So a balanced three-phase systems has relativities, and for this one, it is introduced by our monitors, as mentioned, right? Yeah, why is the three-phase definition used for in a more easier way? I'm not sure whether this page.
The single bus transmission used for electric train illegal point.
Okay. So I guess it's in the following page. So in these three features, in the features of the balanced three-phase systems, of course there is an unbalanced three-phase course. So either of these three can be no longer exist in the unbalanced three-phase systems. And here is the Y connections, right? Three source.
Yes.
Yeah, the maybe it's generally it will be the voltage sources, also can be the current sources. And three impedance, or we call it three nodes. So, and this is the neutral current. Neutral connections, the connection between these neutral points, right?
Yes.
And neutral, you can see the neutral points can only appear in the Y connections, and in the connections there will be no neutral current or no analysis of these. So this is neutral connections based on the KCL, right? KCL law. KCL law, we will just need to know that the sum of the current should not be zero, and it can only be equal to this neutral current. So it's why the neutral current is equal to ABC, the current in the three phases, right? And in this case, we can see that all the three, the voltage sources should be 1 volt, and without any errors, so it should be 0 errors here. So A, B, C, so it will be the device 3. We can just use the 360 degrees divided by 3, so that will be 120 degrees for this different. For these three different sources. And so here, so the complex power, the total complex power will be the complex power for three phases, right? And it's also this conjugate complex numbers. Okay? Yeah, the advantages, here, right? Why the three-phase machine is more easily? Because it has 3 times. Approximate 3 times, but it's actually will be 2 and 2 and 2.5, 2 and 2.6 2.7, 2.8, but we're just approaching the 3 in the real world. And everything we're just having some losses, so the efficiency is very important. Yeah, our analysis. Okay, so this is the 4 advantages in the 3-phase powers. So that's why we put the 3-phase powers will be the major nation of our power systems in most countries.
Easy.
Yeah.
Easy to the machine.
Yes, it's for us. And so this is the Y connections, right? Y and delta. So in Y connections, let's see, because there's 1 circles, it would be the 3 and 15 degrees, and so 1 and 20, 1 and 20, and if we just assume that this is A in the zero, and so it would be the positive 1 and 20 degrees, and this is negative 1 and 20 degrees, so this is the magnitude for leading, right? Leading. And so in the Y connection noise, there are 2 different forms of the voltage and current, right? So the line voltage, so the line current, so the phase voltage and the phase current, right? What do I see this? Here. So and in the Y connections, so this is the phase current, right?
Yes.
This is the
Phase.
we call it the phase, that's not here, right? It can be either the source or the node right here. And for the lines is the connection between the source and line here, and here. No, here. That we were not just going to analyze this neutron lines here. So in the Y connection system, so you can see the source current is equal to the phase, and also equal to the line current, right? Because there are no other branches here. But for the voltages, so this is the phase voltage, right? And line voltage, we know that phase voltage is from this here 3 point to the neutral point, so the voltage here. And line voltage, we will see that this is the voltage difference between the 2 lines, either 2 of the 3 lines. So here, up here, right? There will be 3 line voltages. And you can see for the line A and B, right? Here and here, it should be the voltage over here, right? So where these were not equal to the phase. Yeah, so the line voltage and the phase voltage will not be equal in the delta, although in the Y connection systems. So this is the vectors. We can see that it is Dn, A, N, and Cn. So this is the phase, right? This is the phase voltage, and so this for this way, and it should be the line voltages. So that's why I will say that. So that's why I said that the geometry can be used to solve some of the questions in our English classes. So you can see that the VAD is the VA minus VDN, right? AD, this one, right? So we can use this specific. Okay, so here we assume that the A is just the awkward angle with the specific angles. So connections, the absolute value, or you see the magnitude of the voltage, right? So the line voltage is square root of the 3 multiplied with phase voltage, just in the amplitude or in the absolute value. So in some cases, if the angle is not required to analysis, you can just use this. It's quite easier for you just to calculate and to solve the problems. And of course, right, you can see that all the three. Oh, okay. So because in this system, we assume that this is a balanced system, so that the phase voltage is all equal to the same value. So ABC, you can say that this square root of 3 multiplied with this phase value, or the phase voltage, right? But with the different angles, you can also see this with the 30 degrees, right? As long as you can, if you have this voltage vector figures, you can just do calculate everything. You can just do this because, yeah, this y, the length of this and this is equal, right? So here is a 30 degree, 90 degree, and this is 60 degree. And you can use also the geometry just to see why there is the square root of 3 times of the phase value of phase voltage equal to line voltage. Okay. Okay. So. Okay, so this was from here to here, right? Yes, it's one of the easiest steps to establish just to view this voltage figure, right? Okay, so let's see the angle. The angle of this. This is 0 degree, right? Here is 1 and 20, right? Because this one is equal to here. Because yeah, this here, this A and phase B difference between these two voltages will be 1 and 20, right? So this is 1 and 20. This is 1 and 20, right? Oh, this is 1 and 20, right? This difference between these the two voltage lines is also the 1 and 20, right? So this is the 60 degree. And so this is a 30 degree, right? And this is 30 degree leading, so that's why it will be positive 30 degree. So this is how this angle is come. Okay? So you know the square root of 3. So this is the 30 degree, right? So the cosine 30 degree, right? Assume that this is the 1 is equal to 1, the length is 1. So here, right? Here is the square root of 3 and divided by 2, right? And for here, it will be also same thing. You can see here, yeah. And this is, so this is the amplitude of this voltage. And in some problems or even in some questions, so that's why I will just suggest all of you guys to analyze the angular and the attitude separately. You do not need to just to calculate this all how to just calculate this, or if you have the calculators and very powerful calculators, it's okay. But in this case, if you have your handwriting, you're just calculating by your hands,
Maybe.
so it's very easier to understand that they have this figure and some very geometry because everything is in balance. Okay. So this is why we for the each element of the wire connection, the phase voltage, right? So the device can be the source or the node or the node here. So also okay. Yeah, phase current, phase voltage, the line. Yeah, the why we put the line voltage is also called the line to line voltage. So the line to line voltage maybe is much easier and more specific. The voltage between the line and the line, right? The line current is the current just to flow through the connection line between the source and the load, right? And so it's in the wire connections, so the current is the same. So it's very easy to understand that because there is no other branch here. Yeah, here, here. So the wire current is the same. But the voltage here and here, yeah, you cannot say that it is equal to this, that is equal to the voltage here and the voltage here, right? So that's why we use this just to get the square root three times the phase voltage, and also the leading 30 degrees. You can just do A the extra the 30 degrees. Even if the angle of the A phase is not equal to 0, right? Just like if the A and the phase A, the voltage phase A, we assume that it is equal to the 60 degree. Right, then the V9 of the phase A is equal to 60 and the 30, which is 90 degree. So just to rotate. You can rotate this, okay? It's okay. Everybody understand this? So we're just going to the delta. Okay. So the delta connections, the triangulars here, yeah, you can see that this is a line, this line, this line, and okay, so in these figures it's only showing the node here. But actually the source here is also same directions. Something like this, right? This source side is also the triangle, so there's the delta here and this is the delta. Okay. Okay, so in the delta connections, we're going to see that the line voltage, right, the VA between the line A and line C here, VAC, right, is equal to the phase A. So that in the delta connections, it will be opposite to the Y connection. So the voltage is the same. The line voltage or the 99 voltage is equal to the phase voltage, right? But in the power range, we can see that the power range of VC here, some of it is known as this, right? This is the power range from C to A, and some is equal to the power range from B to C, right? With the condition. So this is why we put power range. Power range is 9 power range. Just to use the power range from A to B, and there's the power range from C to A, right? So we can just also use these reactor figures that we calculate that. It's also the square root 3 times the magnitude, but here is 330 degrees magnitude. You can see that. Also, just remember that the V9, right? V9 is this is the Y connections. So feeds to the line, right, and the leading. And for Delta is also the feeds to the line, but in the power range, and it is negative 30 degree. Get that? Okay, so it's okay. So the power range, yeah, it's power range A, B, C is also calculated in the same way. And for here, the total complex power is so the total complex powers in all of the 3-phase systems, no matter if it's a balanced or unbalanced, no matter if it's the Y connection or the delta connection or just like some different other connections. So just to use the power of the 3 phases, just to add them together, and you got the total complex powers of the whole system. So here, because it's in the balance, so the 3 times, just use this 3 times of the line only. Okay, so and you can see this is the conjugate complex number of I, right? So yes, for the Y, just like this, just like this, angular expressions, representations, something like this. Okay? Positive 30 degree is the conjugate number of the negative 30 degree, and this is keeps the same value. Just to convert the angular over this the imaginary part of the sum of the imaginary part. Okay. Okay, so I'll show you one examples. So the word is the Y, this is the Y, this is the delta connection nodes right here. And so, does everybody know this is what connection?
Y.
Yeah. So, let's notice that as long as all the 3 phases is connected in the same point, this is the neutral point, neutral point, and grounding. So, it can also be the Y connections. So here is the same expression. This is the differentiation. Okay. So it's I can see, right? So this is the impedance in here, and the source is 13.8 kilowatt, the source, right? Okay, so in the first step, we can just get the voltage, net voltage, right? Net voltage here. Yeah, we assume that the AB the angle of the AB is 0, so this is the 9 voltage of this between the different between the either two of the three lines of the systems. So for the for the current of the line current here, right? Line voltage is divided by this impedance, right? For the divisions, the angle is using the manner, right? 0 minus 20, minus 20. And this is because this is kilo, right? Kilo 3 0 2 0 2 0. So this 1 0 here. So it will be 138, right? And just to use the minus 20,
Because this is the
minus 120, and here's 8 extra 120. So, okay? Quite easy, right? And so here, so this is the phase, right? This is the phase current. Phase current, because this is a balanced system, right? So we can use this, the very preliminary method to calculate this is the difference between the two line current, yes, in the phase, and for the 20 and 100 degree, I think the geometry method will be a bit difficult, so you can use the calculators, okay? Or you can just use this the square root of 3, right? Square root of 3 just to multiply with this amplitude, and then, right? Then 30 degrees negative, right? And also you got the current. You get the line current of the A, or you got the phase current of the A, and you can also get the B and C in the same way. Okay? Yeah. It's okay for you. If you would like to use this method, it's okay. Or you can use these conclusions here. But to remember that this is only used applicable for in the balanced system. If the system is unbalanced, no, this equation does not exist anymore. So the total complex power, right? 3 times of the complex powers of each phase, right? 3. This is the voltage of the line voltage A and B, and the conjugate complex number of the current between the A and B, right? I say that so is minus 20 to the positive 20. Pretty easy, right? This is the kilo, so here is the 1,000. That's angle is the 0 at 20 here, and 3 here to calculate this. And you can use your calculators just to express in the phase representation. So this one, you cannot just to finish it in your hand. It's very difficult because it's 20 degrees. So by doing this, we can say that the power factor, you know what is the power factor? Can you remember this? Yeah, here, okay. Phi is S is T, right? The cosine, phi. So the cosine 20 degrees. So then just add these power factors. Okay. Okay, so I just wonder if I were to provide you these just like these problems in the examination, and just to find it out. Difficult? I think it's not a bit difficult, right? So in some cases, I can present you some of the equations or some of the necessary information, okay, but you cannot get everything. Just you need to write down the steps between this and this calculator, okay?
Okay.
So I think this is quite easy.
Lakshmi, I have a question. Actually, I vehicle but we use minus.
You mean this?
Yeah?
Why minus 20?
No. IAB minus, right? But we use what is minus?
Oh, you can say this
Yes.
because yeah, please notice that here is star samples. Star samples are assembled here. This is the conjugate number. The previous voltage is 100 degree. Okay, this match. Okay, and it's doing like this. It's current, right? And we call the conjugate of this current conjugate complex. Yeah, 工作复数. Yeah, it's Chinese, right? It's just to keep the magnitude of this
Same magnitude.
same value, but the negative value of this angle. Right? Okay. Let's do this. This is the star symbols here. Okay, so you can see in the angular form just like, and this is the current, and for conjugate is okay. So just do it's minus 20 and the positive 20, right? Or in some cases just like in the phase angle, just
Two minus
minus converge this
conjugate.
angular or just symbol ahead of the imaginary part. Okay? So just doing like this, do a star. So no stars is also the minus. So this is a Delta-Wye transformation. Okay? So in the dynamic sequence, so the impedance of one phase is okay. So we see that, and the impedance of the one phase in the delta connection is 3 times of the Y connections, and for the phase is equal to the. So we just to analyze this in the previous graph, you remember? Okay, that's this. The square root of 3 in the magnitude and 30 degrees leading that in the voltage. Okay, so here is a simple delta to Y connection transformation proof, right? We would like to transfer the delta to the Y. Yeah, in that case, you know everything in this delta connections. You know this d delta, and what you need to do is just to calculate what the Dy is equal to. It's quite easy in the balance situation, right? So in the delta, so that we have this this line current here is equal to this minus this, right? Because this directions we equal this is the clockwise, right? So this is the clockwise, and this is this is the inverse counterclockwise. Right? This is the clockwise, so it's A, so it's out, in, this is out, so this in, positive, out, negative, right? Of course, if you use this using the counterclockwise, positive, negative, it's okay, it's up to you. So just doing like this, right? So this is the difference between these two line voltages, and then divided by this impedance. So we can just use the current and voltage to represent the impedance, right? So for the Y side, so this VAB, right, is VAB. So you can say that it is Dy is multiplied with the difference between these two phase current, right? AB is the current, right? VAB, right? So we can also get the same in the same process. We can get this V and 9 voltage between the C and A, the 9 voltage. So the difference between these two 9 voltage, right? We can just write down like this. Phase A current because it's the minor, so phase A minus negative phase A is A, the phase A, right?
Yeah.
Minus phase B, and minus phase C, right? This is like this. Because this is the balanced, right? So this ABC should be equal to 0.
The neutral voltage.
So in the unbalanced systems, there should be a neutral line, right? So if there is no neutral lines, it must be a balanced. So you may you know that some of the current cannot be still in line, right? The energy should be in the balanced. Okay? So doing this, we can use this minus current phase B minus this current phase C to represent the current of phase A, right? Okay, so using this into these equations, right? Use these equations here. This is the current of phase A, right? So the 2 and extra 1, 3 current A and Dy, right? And you can see 3 Dy, just use this, but both sides divided by the current phase A. So here is clear, and you can get the Dy is here, right? V delta. V delta is here, right? Because we got V delta is equal to this. So 3 Dy is equal to 3 times Dy is equal to V delta. So that's why the this impedance in one of these of the Y connection is equal to the connections, the impedance node or node there, is like that's 3. Okay, so this is the 3 is mine, right? 1, 2, 3, and this 3 is here. Okay, so yeah, if you prefer, so Amber. Okay, so in that case, so this proof is only for the balanced system and with the identical right impedance in each piece. So what if the impedance here is not equal? Right? So so you know the equations, but you know how the equations come from. And do you have some advices how to just convert this to this?
Can I write? Can I write?
Of course. No. I think you do not need to calculate this in details, but do you have some idea that how to do this? Just basic ideas, or convert this to this? So what we need to just use the RA, use this 3 to express. You have some basic ideas. You do not need to just do writing everything because I will do it for you. So everybody have any idea about this? Okay, so I will give you one very simple basic idea for this. Just if we would like to use calculate this one, let's to catch one of the sources. Catch, right? So in that case, there is no voltage is here, right? So in this case, this should be doing like right? It's a parallel connection. Yeah. Here, because this is a big charge, right? And for y is very simple, right? Right, because this so speed has been charged. No voltage on the impedance B, right? So it's useless because there is no branches here just to make a connection. Here to here, right? And if this two we would like to convert this to this, so we have to calculate the impedance from here to here, so the total impedance, right? So to be RAB minus 8 RBC equal 1, and RAC, so 1 divided by this, and this. This is our delta, right? Do you understand this? It's a parallel. It's a parallel connections, and if we would like to calculate the total impedance here, right? 1 minus this 2, 1 divided by this 2, 1 divided by this 2, and we do H, and then it's equal to 1 divided by the R delta. R delta is the total impedance of this current, right? And for this, it's quite easy. So RC is equal to RY. It's a theory connection, right? So it's A, Y, and B. For here is can calculate the R delta, that the total value of this, and this 2 is equal, that we would like to transfer this to this. So R delta should be Ry, that understanding, right? So this is we would like to make this part and this part R delta is equal to Ry, right? Because we transfer from this to this, so this 2 should be the equal value, right? And so since it's no room, so it's in the same way, right? We can just do then part the C, so the source in the phase C. Next, finally we just to cut the source in the phase A. There should be another 2 equations like this, right? So in this, by these 3, only the unknown variables, because we have known this delta, the value of the delta connection systems, right? This 3 is the known variables, right? This 3 is the unknown variables, right? Yeah, RAC, and if we touch the phase B, it should be the RAB. If we touch the phase A, it should be the RBC, right? The total will be 3 unknown variables, and we have also had the 3 equations. So in the mathematics classes, we know that when the number of the unknown variables and equations is the same, so all of the unknown variables can be solved. Then we can just do calculate the RA is equal to 1. Expression by this 3, RB expression by this 3, RC expression by this 3. So this is what your equations come from.
From here.
Yeah, from here, right? And of course, if we would like to convert the Y to the delta, right? Then these 3 are the unknown variables, our target variables, right? These 3 are the known variables, right? Can also use this, right? Because also is going to be 3 unknown variables, right? And this one is maybe a little bit more difficult because but 3 unknown variables, 3 equations. We can also just doing that. Just this one is called RA, then RA is equal to what, and here is the RAB is equal to what. So that RA is expressed or represented by these 3, and from if we would like to convert this Y to the delta, it should be the RAB is expressed by these 3. Okay, so just doing this, all of you are in these 6 equations comes, right? Of course, so in examinations, if there will be some questions, we're using this, I will present you. You do not need to just to remember all the equations. Of course, if you can remember or if you can memorize some equations to be much better, because you can just to finish your questions more quickly, right? Okay, so I think it would be very easy just to cut. Oh, God. Okay, so we will not have the 10-minute break between the first and second class, okay? So, and I can be sure that all of you can just do finish our class in the 11:30. Okay? I guarantee. Okay, so we can just to discuss more detailed information about the three-phase systems and the mass natures of this. Okay, so the same if after so it means in the balance three-phase systems, so the analysis for the each phase can be used in another two-phase system like this, because if the balance order of these equations is business, just divided by 3, it's quite easy. So for the balance three-phase systems, we know this is the base assumptions for this analysis. So the all nodes axis is one connected in the Y connected and no mutual inductance between two phases. So maybe in the next class we will just to learn something about the transformer, so magnetic field. So in that case we will actually, so the impedance of the phase A may affect the impedance of the impedance in the phase C. So when is the mutual inductance between these two phases? So in today's class, we assume that there is no inductance, no mutual inductance here. So these are some assumptions, right? So decoupled, it means there be zero mutual inductance. The phase A will not affect the phase B and C, right? Okay, for the third point, there should be 3 sequences in the power system analysis. So the positive, the negative, and the zero sequence, right? So I would like to state that at first that all the 3 sequences, the zero, the positive, the negative, and zero sequence is actually does not exist in our real world. So it's in our imagination. So it's actually needs to be more convenient for us just to analyze the 3-phase system. So you can just know that the sequence order everything using is just to made by human. We need this sequence order, just like for example, so the phase B makes phase C makes phase A, right? So so this is A, B, C, right? B net A, C net B, right? But if what we use B leading A, B, C leading D, right? And you can just have the base information, information for this for the positive. And this is for the negative. And this is just the different definition of this 3 phases order, right? For the zero is quite specific. There will be A, B, C, there will be no differences. They are all in the same directions. It's for the zero. Right, so maybe we are just to discuss it later. Maybe we just learn the power flow. Okay, so let's have base here of this positive, negative, zero, and all of our analysis 3 phases is the positive phase B, C. Okay. So this is the analysis for So the first step to convert delta to equivalent Y connections. That's what we're doing 7 days ago. You use these equations. So all equations you can just to use directly. If we use that to solve some questions, that to create the version, the conversion of these. So we can use the solve the phase A independently, just like we charge the phase B and we charge the phase C, right? The same starting same procedure will be the same base ideas for doing this. So the total power, right, in the balance system is 3 times of the each compressed power of each piece. So B and C, so it can be used for inspections because B and C should be in the same amplitude or just like a very nice formula shift, the phase shift, right? A, B, C should be the 1 and 20 degrees shift. Yeah, if your answer is exactly the 1 and 20 degrees, yes, I think this program you can just do very correct answers, absolute correct answer, right? Okay, so the final step is to use the two original circuit to determine so non values or the internal values. Okay, so just have a take a look at these steps. And show you some typical examples. So it will be the final examples of these natures. And this is doing like this, right? Okay, so there'll be so many assumptions here, right? The Y connect with generators, the sources, right? This Y connected generators with the voltage of the 1 volt and with the 0 degrees, right? Voltage supplies. So this generator is applied to a delta node. Here, right? The impedance in the delta node is the minus J. Here is all the same value, so it's 9. And so in these assumptions, we assume that there is a loss of the transmission lines. So you can see that just a impedance here. So the load is also connected to the connected generators. So there will be 2 generators A, B, C for this. A plus plus, B plus plus, and C plus plus for this. So there will be 2 set of generators or voltage sources. So it's also the 1 and 0 degree, 1 volt and 0 degrees, transmission line, the same transmission line impedance with 0.1 J, right, for this. Okay, so this is the assumptions. And so we need to solve the node voltage, right? Node voltage. Yeah, either one is okay because the order of circuits is the same. And so the total complex powers, right? Okay, so in that case, in our steps, yeah, you can just see the converge in the same connections. Yeah, because you cannot, I think it's very difficult for you just to use this Y connections. You can make this delta, right? It's really much more complex. So in the first step, you converge the delta source to the equivalent Y connections, right? We need just to convert this to this. And do remember that what in the balanced circuit situations, so Z equal to what? That we convert this to the Y connections. Do you remember this?
This is for capacitor.
No. How much is equal to? In the we convert it to the Y.
Y.
Yeah.
Mm.
Okay. Do you remember this? It's the simplest way because all of this is the same value and it's the balance. Okay. So don't worry.
RB plus RC plus RB RC by RC RB.
Actually, you can use this because this is the same. Okay, so you are answer is for the general ideas is okay, but if the A equal to B equal to C,
To use
this
this one.
this one. It's much easier, right?
Yes.
Okay. You see the memorize is sometimes it's also useful here, right? Just to convert this to the Y connections, right? And if you just draw the A phase, right? You can just use this A phase, right? B and C because in our procedures, you can know that solve the phase A independently, right? Because the B and C is identical, except for some degree, right? Except for these degrees, so we can just use the phase A, right? So that we write down the phase A circuit. So you know how this circuit comes from, right? J divided by 3, right? This is the equations we assure you that in the last lectures. So because it's identical, just divide by 3. A, B, C, right? This is the A. Then this A is equal to this divided by 3, right? Divided by 3, divided by 3, divided by 3. Right?
Mm.
Right? So this is right? And this dy, right? Dy is equal to this term. So this is the next d minus j divided by 3 is minus j divided by 3. Okay? So we only analyze the phase A. So that's y is here, right? Phase A, then we just to connect the neutral point to the ground the neutral point, right? So when the neutral point is connected to ground, so all the current you see are here. In the previous circuit connections, it will be here to here, right? Here and divided by I current B and current C, right?
Yes.
But if we start grounding, 0, 0, 0,
0.
yeah. So actually, if we would like to analyze only one phases, right? That's in the Y connections, that's to a connection between the neutral point and the ground. So short, so it's only A like this. And this is the impedance of the transmission line, right? So this is 0, 0.3, so this is the point, right? Not 0, 0, 0, 0, 0, 1. Okay? So this is 0.1 J, right? And for this generator, systems, okay, those are one source systems. So the voltage for the phase A is the Y connection, right? And this is the Y connection, right? So it can be equal, can be directly send this current from this power to the phase A, right? Something like this. And this is the current A, send this directly. So you can see it's the same value. Okay. But on the right side of the system, so in the delta, so the impedance or the node A, phase A here, its power comes from this and this, right? Both of these two generators or these two sources will send the powers together, right? So in that case, we should go back to the first step, convert, yeah, the delta to Y connections. And you may remember this one. Delta to Y connections. Yeah, the 30 degrees mapping, and this will be 1 divided by the square root of 3, right? Do you remember this?
This impedance.
Yeah,
Z by 3.
this is the voltage, right? I will show you for
Having this impedance.
yes. Make sure you can just do
B line over 3, yes.
yes, okay. Okay, so this phase A, this situation we are just to analyze the phase A. So every parameters you can understand, right? Okay. Okay, so in this very simple situation, right? So KCL law, you know that we can just focus on the A plus, right? At that point, this three current should be, the sum of these three current should be 0. The voltage here, right, minus here, okay. So this is the ground. So the voltage of the ground we were simulated to be 0, right? For this ground, voltage here is equal to voltage minus this one is equal to 0, right? So that the voltage here is voltage A plus minus this voltage source, right? It's the voltage. Voltage is the voltage for the transmission impedance, right? And so we're going to have to use this one because this is right. So divided by the 0.1. Okay, so it's going to be okay. So the y here is minus 10, and this is 0.1 J. Okay, because this is minus 1 is equal to 10. And up here, you can see that's the voltage here, and divided by the 3, divided by the J, divided by 3, right? Just like the 3 times, multiplied with 3 times J. And this is the current here. And for this, the current is voltage A plus minus this is the voltage A to this transmission impedance, right? What I was saying in transmission impedance. So everybody clear about these questions? don't worry. So if you have some questions, okay, you can just to let me know. The old law, right? The current is equal to the resistance. Okay, so here it should be impedance, right? It will be the voltage, it will be the voltage divided by the impedance, right? Impedance is 0.1, right? And 0.1 and 1 minus 1 divided by this is 10, okay? And so for the meters, this is the direction, right? This symbol, negative or positive, you can use your own assumptions. You can just assume that all the current is out of A plus, right? Or you can just assume that all this current E is in the A point. It's okay.
So like a seal, no diaphragm. Tap like a seal there, in this middle point.
Oh yes, it's okay. Yeah. So in this, we just assume that it's negative, that's why it's negative. So it's about your assumptions. Okay, so like you just will solve these equations. Solve these equations. Okay, so this is your parameters. So maybe a little bit difficult, but you can have to calculate this and to reform this equation to like this, right? And back to back is 10 multiplied by J, and this 20. J minus 3 is 70, right? 70. Okay, so anyway, so we can use this convert to the imaginary phase domain and use this. Anyway, you can just to solve the value of the voltage in the A plus, right? Because it is here. Okay.
Polar is angular format is okay.
Okay, so the phase representation or the angular representation is up to you. Both works for the rest of course in the examination. Okay, so the same thing, B and C. And you do not need to calculate this because this is a balance with the identical impedance, right? Minus 1 and 20, right? They need extra 1 and 20. So this is not very so difficult, right? So in some cases, if you would like to make sure that your answer for the B plus A is correct, you can use the sum method to direct calculate the voltage of the B and C to see if the voltage of B and C is just like the difference of this angle is 120 degrees, so everything is okay. But if you do examinations and you are so confident for your calculators, I think they are very good, very expensive calculators, so you can have to use this BA and to get the B and C. So okay, so of course this GPT I will just send you the group chat. So just to write up the important part will be
This is balance.
balance, right?
Zero.
Yeah, I think. Of course, it should be the same magnitude and just like 3 directions, maybe balance directions. Okay. If the answer is not incorrect, I'm not sure. Okay.
If this is not correct, maybe we need a neutral line.
Okay, so let's take some summary or conclusion of these operations. So in the system analysis, one of the goals is to provide the inductive figures for power operations. impact of the transmission systems into the base flow, power flow. The power flow we just to discuss later. Okay. Okay. Let it go. So this basis, this is the base of the power system. So for all the three major points, so the generations, the nodes, and the transmission. So actually, you can see all of our discussions about the power systems generation, nodes, or to convert load to the impedance, and the transmission, right? So all of the networks is working about this. The generations, the power source, the nodes, the consumers, and transmissions to transfer the voltage power, right? Yeah, and this is there's one major difference between the distribution system and transmission systems. So this is in Americas, it's going to be divided by the 100 kilowatt. Okay, so in China, yeah, it should be 100 kilowatt because we call the 1 and 10 the transmission systems, and maybe the 35 is the distribution systems. So this is the power word, right? If you need to use it. So in the power word, although actually in some real applications we're using this one-line diagrams, right? We were knowing that in the diets, in the lectures.
Bus 1, bus 2.
So I'll show you in something maybe your monitors is familiar with this, but if you do not use the power before, I'll show you. So green arrow, right? This is the node. It's not green arrow, it is the amount of this load. So it's also in the direction, or it indicates direction or not direction.
Load
No?
yes.
Okay. So actually I'm not I've never used the power before. So the type chart, right? Type chart it shows the real and reactive power flow, right? And this is the megawatt for the reactive power, and the megabar for the reactive power, right? Which are clear for you to.
This is the loss.
Yeah, of course the loss, right? Because the things.
Yes.
The active is below the zero line, below the x-axis, right? So it's a positive, right? And so this red rectangular is sure in the circuit breaker. So the circuit breakers, the function of this is that if you say the generators, okay, so there will be a heavy magnet or high. This magnet to keep this generator so it does not work, right? It doesn't work. So these two, and these three generators just to cut this line, okay? So to make sure that all the power systems, the major part, the other part of the power systems will be received and steered in the operation, right? Part. And in that case, only these nodes, only this small amount of consumers will be affected. But if there is no security breakers, well, here, everybody will get in voltage. So this is the voltage here. It shows the periodic values, the nominalized. So do you know the periodic?
Power unit.
Yeah, actually it's also an artificial. It does not exist in nature. So per unit, just like 1 per unit, it's quite very easy to understand. It's actually a human-made standard to estimate some important values, just like, for example, if you choose 100 volt as standard back, so that 200 volts will be equal to 2 per unit. So this is for the normalization. But of course, the 100 volts is your standard. You can also use. If you use the 200 volts as your standard, it means 200 volts is 1 per unit. Okay, so it's just for the easy access to analysis, right? So this is also the same. This is the bus, right? This is the bars, and this is the active and the reactive power. Home areas. So this is the control output. So this is generator, right? This is generator. Doing like this. This is the arm shell. Here's something like. And this direction of the arrow. Okay. Oh, okay. So it is stated here. It's the direction of the line and the direction of the power flow, right? Power flow from here to here, and rather than from here to here. It's actually so I can get to give you a very brief introduction about the power flow. Power flow is what? It's just the flow of the power. Very easy, very examples to understand, right? Okay, so things down. So this is a very simple sample power systems. Yeah. One moment, only 3 pages, okay? Okay, so we can do previous lectures. Trend. Okay, 1 moment. Okay, so I've lost 5 minutes. So the top trends, right? What is the top trends? Very easy. Okay, so transmission line. Yeah, you can merge that to. Okay, so you transfer 1 gigawatt, 10 gigawatt, and 1 gigawatt, 1,000 gigawatt. I forgot about this. Okay, so 1,000 gigawatt. So do you know this transmission line can this such a high voltage, right? It cannot. So it's pretty easy. The balance constraint, right? The power flow transfer. So this power flow should be obeyed. So the KCL laws should not be should keep the balance noise. So also the power will be some loss in the transmission systems, as that is the impedance in the transmission line in our previous example, right? Control, okay, control, if you have interest, you can just do more time in our maybe lectures later, because power control is achieved by control the power flow. Okay, transmission line limits. Okay, so this will be power flow. So limited by the heating considerations is actually when you transfer the 1,000 gigawatt in the transmission lines, boom. The transmission lines where to notice this because there is a heat, right? The loss of the power is the heat will burn this transmission lines. So but there should be some problems for the transmission lines, so there will be a limit, right? So you cannot transfer more powers than these limitations. But in reality, the transmission lines there can be a little bit higher or see the limit, but maybe near almost no more than 5%. Yeah, if you add an extra 50%, I'm going to make sure that the transmission lines will disappear. So the owners, okay, transmission owners, okay, so showing this is overloaded, right? This is, you can see that the 29% right means large, right? Very dangerous. Okay, thank you for watching. We will meet at 10:30. Okay, you have the best. Have a great.